So in this lecture, I want to discuss Zorn's lemma. And to state Zorn's lemma, I will need some definitions. So I have a set X, and I have a relation R in this set, which means that this relation concerns two elements, and I will assume that this relation R, it's a partial order. So this is the definition of a partial order. So partial order, it's a relation R, which satisfies some properties. And if you want to have an example in mind, think of you have a set omega, you take the subsets of this set omega, and you define the inclusion. So you say that A, it's related to B if A, it's included in B. So this is the example you need to keep in mind. So I would say that R, it's a partial order if, well, it is reflexive, which means that for all x in X, X, it's related to X. So indeed, A, it's always included in A. Then it's antisymmetric. In the sense that for all x and y in X, if X, it's related to Y, and Y, it's related to X, then X, it's equal to Y. And again, if you have a set A, which is included in B, and B included in A, then A and B are equal. And finally, it's transitive. Which means that for all x, y, z in X, if you have x related to y related to z, then x, it's related to z. And again, in our example, if A, it's included in B, and B, it's included in C, then A, it's included in C. So if you have a relation defined in a set X which satisfies these three properties, you call that a partial order. And this partial order will be called a total partial order if you add a fourth condition, which is the condition D. So this is an extra condition, and if your relation satisfies also this fourth condition, you say that this partial order, it's actually a total order if for any x and y in X, either x, it's related to y, or y, it's related to x. You see that the inclusion is not a total order, well, because let's say that you take omega equal to n, you take a set A to be, say, the set 1, 2, B, the set 3, 4. It's not true that A, it's included in B, or B, it's included in A. So in this example, this relation does not satisfy condition D, and therefore it's not a total order, but it is a partial order. So here's the definition of partial order. If I add this fourth condition, I get the definition of a total order. So let me give you a second example, which it's quite useful. I'll consider R2. And from now on, instead of saying that x related to y, I will just say that x smaller than y. So I'm using this to indicate the partial order relation in a set. So as I said, I consider points in R2, and I will say that a point x1, x2 in R2, it's less than the point y1, y2, if and only if x1 is less or equal than y1 and x2 is less or equal than y2, where here I'm using the usual relations in R. So visually, it means that here's my point x. It will be less than the point y if this set is contained in this set y, which is y1, y2. And this is a partial order. You can check that these conditions indeed satisfies the three properties of a partial order, and just observe that it's not a total order because these 2 points are not related one to each other, right? It's not true that this point is smaller than that one and that one is smaller than that one because no sets are contained. So that's a very good example to keep in mind. And I will introduce two concepts, two definitions. The definition is, well, now assume that you have x. This x is endowed with partial order. And I will say that you take a subset of x. A point z, it's called an upper bound. For a, if x it's related, it's smaller than z for all x in A. Right? So a point z is an upper bound for a set A if x, any point x in A, it's smaller than z. So in my example, in R2, if you have a set, here is a set A, well, any point here, it's an upper bound. So any point here whose second coordinate it's above this value and first coordinate it's larger than this value will be an upper bound for that set A. And note that, well, upper bounds are not unique. That point will be also an upper bound for this same set A. And now the second definition, it's about maximal elements. So I keep x with a partial order, and I want to define what's a maximal element. So I have a set A included in X, and I will say that Z in A is a maximal element if the following property holds. If you have Y in A and Z is smaller than Y, then Z it's actually equal to Y. So a point Z it's a maximal element if any point Y in A which is larger than Z has to be equal to Z. So there are no other points, there are no points Y in A which are larger than Z. Of course, there might be points which are not comparable with Z. So let me just give you an example in R2, for the same partial order I just defined. If you consider this is my set A, well, all points on the line, and let's say that A includes all this line, all these points are maximal points of A, right? If you take any point in A which is larger than that point, the points which are larger than A all belong to this set. So the unique point which is larger than this point, which belongs to A, it's exactly that point. And of course, well, there are more. In this example, you have an infinite number of maximal points, and you see, well, that you have points which are not comparable with these points. So I'm not saying that all points are less than z. I'm just saying that, well, if a point is larger than z, then it has to be equal to z. So this is the definition of maximal elements. And now I have all definitions I need in order to state Zorn's lemma. So here's the statement of the Zorn lemma. So again, we have a set X, which has a partial order, and I'm assuming that X is not empty. So assume that any totally ordered subset y of x has an upper bound, or admits an upper bound. So this is the assumption. You have a set which has a partial order. It's not empty. And assume, so I will come back to what means a totally ordered subset y. So assume that you have that any totally ordered subset y of x admits an upper bound. Then x has a maximal element. All right, so I will not prove this lemma. You will find in the comments below reference in which you can find the proof. I'll just mention that Zorn's lemma is equivalent to the axiom of choice. So if you start from the axiom of choice, you can derive Zorn's lemma. If you start from Zorn's lemma, you can derive the axiom of choice, which is used in measure theory. And so I won't give a proof. I just want to comment about this assumption. So a subset Y will be set totally ordered well, if this relation restricted to the set Y satisfies condition D, which I stated before. This means that for all x, y in Y, x is smaller than y, or y is smaller than x. And let me give you an example. So again, let's return to the space R2. If you consider either a line, so let's say that this is my space X. So this set, it's clearly totally ordered because, well, if you take any 2 points in this set, one it's larger than the other one. So any line here, it's totally ordered. But not only the lines, but you can also define a path which is, say, like that. And here's my space A. So that's that path. It's also totally ordered. If you could take any 2 points in this path, one it's smaller than the other one. And well, this is an example. If you consider, so if you consider the space which includes the line as my space X, this is a space which satisfies the condition of Zorn's lemma. If you take any totally ordered subset, it will have an upper bound, and you will be able to choose an upper bound in this boundary of the set X, and therefore there you will have the existence of maximal elements, and indeed we have seen that any point in this line is a maximal element. Well, an example in which this condition is not satisfied, it's taking with the same order the space R2, you can just take a line. This set Y, it's of course totally ordered. If you take any 2 points, one, it's smaller than the other, but this set has no upper bound in R2, so we are not able to apply Zorn's lemma for this set, and indeed this set has no maximal element. So I hope that you now understand what I mean by a totally ordered subset of a partially ordered set X, and that you understood the meaning of this lemma, so that if any totally ordered subset admits an upper bound, then you know that you have a maximal element. And to illustrate how we are going to use this lemma, it will play a very important role in the proof of the Hahn-Banach theorem. Well, let me show you that any normed linear space or linear space admits a basis. So this is my next topic. So to illustrate the way in which we'll apply Zorn's lemma, let me prove that all sets, so X will be a linear space, and I want to prove that X has a basis. So let me define what I mean by a base. A family X theta for theta in some index at I, which can be countable or uncountable, I don't care. I'll say that this is a base of X if two conditions are matched. The first one is that any finite subfamily of this family is linearly independent, which means that for all n, and for all theta 1, theta n in I, which are different, theta I different from theta j, then the set x theta 1, x theta n is linearly independent. So this is the first condition which needs to be satisfied. And then the second condition is just that the span of this set is equal to x. So x is equal to the span of this set. Remember that the span of this set is the smallest linear space which contains all these points x theta. So here I'm requiring that, well, the smallest linear set which contains all these points, it's exactly equal to x. So if these two conditions are satisfied, we say that x theta, this family of elements of x, forms a base of the space x. And what I want to show you is, well, using Zorn's lemma in order to prove that any linear space x admits such a base. So here's the theorem. X is a linear space. X, it's not empty. Then there exists a basis x theta, theta in A, which is a base. And the proof, well, the proof consists in defining a new space, which let's say that I will represent it by omega. So omega will be a new set, and this set will be endowed with a partial order. So let me just define what the set omega is. The set omega is formed by all sets x theta, theta in I, such that the first condition of a base is satisfied, which means that for all n and for all theta 1, theta n in I want x theta 1, x theta n to be linearly independent. So whatever n, whatever finite family of elements I take, they are linearly independent. So this is the condition I impose on the elements of omega. So omega is the set of these families. And this set, I will introduce now an order. I'll say that x theta, theta in I, it's smaller than y theta prime for theta prime in, or y theta for theta in I prime. So I'll say that this point, this element of omega, it's smaller than this element of omega. Well, if any point x theta, it's contained in this set. So for all theta in I, there exists theta prime in I prime such that x theta is equal to y theta prime. This means that all elements of this set belong to that set. And if this happens, I will say that this point of omega is smaller than that point of omega. This is clearly an order. I leave it to you to check that this is an order. And now my second step is to prove that the assumptions, the hypothesis or the hypothesis of Zorn's lemma is satisfied. Right? So what is the hypothesis of Zorn's lemma? It's, well, let me take a subset omega prime. It's clear that omega is not empty because x is not empty. So you take a point in x, you have at least one set, so 1 point in omega. Now, omega is different, it's not empty. Now let me take omega prime, a totally ordered set. So the points of omega prime are such sets, and I'm assuming that they are totally ordered, which means that if I take any 2 points in omega prime, either one is smaller than the other, or the other is smaller in the first one. And I want to show that there exists an upper bound. For this set. So I have to exhibit an upper bound for omega prime. And the only assumption, the only thing I know is that this set is totally ordered. So let me let me construct this upper bound. And the idea is to take the union over all elements of omega prime. So let me construct a point, which is, let me call it maybe z, which will be all x theta, theta in I. And what I want to take is that I want to take the union over all points x theta. So I'm taking, so omega prime, each element of omega prime is such a family of points in x. I'm taking just the union over all these points. So I don't know if this notation is clear to you, but let's say that omega prime, if you want, it's equal to all the points x theta for theta in I alpha for alpha in some set J. And what I'm doing, I'm defining a new point Z, which is the union for alpha in J of x theta, theta in I alpha. So I'm taking any point in omega prime. It's a set of points in X. I'm taking the union over all these points. And now I want to prove that this point Z, it's an upper bound. Of omega prime. So I want to show that if X belongs to omega, then X is smaller than Z. First, I want to prove that Z is indeed an element of omega, because I need to show that the upper bound I just constructed, it's an element of omega. So to show that Z is an element of omega, I must prove that if I take any finite number of elements in this set, they are linearly independent. So let me take, so zeta, it's composed of x thetas for thetas in different sets. So Z, it's composed of these elements. Let me take a finite number of them. So let me take x theta 1 up to x theta n, where x theta 1, it's an element, theta 1, it's an element of I alpha 1, and x theta n, it's an element of I alpha n. But now, since I know that the set omega prime is totally ordered, this means that if I take x theta for theta in I alpha 1 and x theta for theta in I alpha 2, either this set it's contained, it's smaller than, either this point is smaller than this one, or this one is smaller than that one. So let's assume that this point is smaller than this one. Well, if this point is smaller than that one, means that all elements x theta belongs to this set. This means that any x theta can be represented as an element of this set. Now I can take among all these sets the largest one, and this will tell me that the largest, so that all these elements belong to the largest set. And since they belong to the largest set, and the largest set it's an element of omega, this means that the points are linearly independent, which proves that x theta 1, x theta n are linearly independent. So this shows that Z, it's actually a point of omega. So Z is a point of omega, and now I need to show that Z is an upper bound. So that Z, what I need to prove is that if you take x in omega, then x is smaller than Z. But to show that x is smaller than Z, what I need to prove is that take x is point formed by elements. So it's a set formed by elements of x. So it's a set of x theta for certain theta. But in the way in which I define Z, I included all these elements. So it's clear that all these elements which are present in X are also presented in Z, and therefore that X is smaller than Z, which proves that Z is an upper bound. So I hope that I convince you that omega endowed with this partial order is satisfies the hypothesis of Zorn lemma, and therefore, by Zorn lemma, this means that omega with this order has a maximal element by Zorn lemma. So I will erase everything and just keep the fact that omega has a maximal element. By Zorn lemma, so omega with this order has a maximal element. So let me call X this maximal element. So X, it's a family X theta, such that theta belongs to some set I. And this point, it's a maximal element. And now I claim that X, okay, so let me just write this as X, not to mix the notation with the set X. So I claim that the set X is actually equal to the linear span of this family. Well, we have to show this identity. It's clear that the linear span is contained in X. So what we need to prove that X is contained in this set. Well, I assume it's not. Suppose this is not true. So suppose that there exists Y in X which does not belong to the span. Fine. Well, if this is the case, let me include Y in this set. So let me consider now the family Y union X theta for theta in I. Well, I claim that this family is linearly independent. And why is it linearly independent? Well, that's clear. Well, if I consider a linear combination of elements X theta, I know that they are linearly independent. I just need to check now that if I include Y in this family, I still get something which is linearly independent. So let me take alpha Y plus Yj X theta j. Let's assume that this is equal to 0, and I have to prove that all coefficients are equal to 0. First, I claim that alpha, well, if alpha is different from 0, then what I get is that if alpha is different from 0, we did that already, I can divide this equation by alpha and get that Y, it's a linear combination of these elements, and therefore that Y belongs to the span. But I'm assuming that Y doesn't belong to the span, so alpha has to be equal to 0. But if alpha is equal to 0, what I get is that this sum is equal to 0, and I know already that these elements are linearly independent, so I get that also all alpha j's are equal to 0, and therefore that this family is linearly independent. So I get that this family is linearly independent, and now I get a contradiction because this set, this point, is a maximal element. Well, but this point, it's smaller than that point, and they are not equal. So I obtained a new element which belongs to omega, which it's larger than X and different from X. And this is a contradiction with the property that X is a maximal element. So, which means that if X is a maximal element, the set X has to be equal to the linear span of this family. And this proves that, therefore, that X has a basis which is given by this family.